First and foremost, a warm welcome. This is going to be a fun video. We're going to cover the TFT model architecture. So take a deep breath, close your eyes, and ta-da! Here's a big shiny equation for you. Now, I'm going to cover this step by step. So let me break it down. The first one, so y at time I, so the predicted value for the ith time series, at time t for quantile q at forecast horizon tau. And I know that this is tricky, but again, predicted value for the quantile, because we have this with quantiles in TFT. It's not mandatory, but it's about the probability of predicting something. And then we have forecast horizon tau. As we have shared, when it comes to TFT, you may have multiple time horizon forecasting. Then we have the f of q. First, the function used to compute the quantile forecast, and this function takes several inputs to generate the prediction. The first one would be tau, so the forecast horizon, representing how far into the future we are predicting. Then we have the y at so the historical target values for the ith time series, and this represents the past observations of the target variable. Then we have z, unknown inputs, also known as past covariates, for the ith time series from time t minus k to time t. And these are inputs that are known only up to the current time step and include variables like past weather conditions, past sales, so stuff that we know what has happened, but we don't know what will happen in the future. Then we have known inputs, also known as future covariates, for the ith time series from time t minus k to time t plus tau. And these are inputs that are known in advance and include variables like holidays, day of the week, scheduled events. And then we have static covariates for the ith time series. And these are features that do not change over time and provide context for the model. Location, type of product, like anything that's static does not change over time. Therefore, when it comes to the forecast, we predict for multiple time series forecasting horizons. So this will be the tau. Then as well, we predict in quantile. So we have this confidence interval. And there's historical inputs, unknown inputs, and known inputs, and the one that was missing here, the static covariate. And all of this is then bundled together. Now, if you thought that this equation was a whammy, now here comes a double whammy. And P.S., a whammy, according to the dictionary, is an event with a powerful and unpleasant effect, a blow. So here we go. This is the actual diagram from the TFT model. And this is the main goal for this lecture, to master this framework. Of course, again, if you have any questions, do hit me up. This is not easy, right? So this is massive. So we're going to take it step by step. I'm going to try to explain everything one by one and see how it builds on each other. And hopefully it will make sense. If it doesn't, come to me. I'm here to help. We're going to start by just looking at x t plus 1 first, and everything starts with a variable selection. This is similar to any model. Like, this is your inputs. This is how it starts. Then the variable selection moves to the LSTM decoder. What does it do? The LSTM decoder takes in the processed information from previous steps, such as past data and known future inputs, to generate predictions for future time steps. It receives encoded information, processes it, and predicts future values step by step, leveraging its memory to consider both recent and long-term data. Finally, the add and norm gate is crucial for maintaining the stability and efficiency of the network's output. It works by combining the output of the LSTM decoder with the input from a previous layer through the residuals connections. And this helps preserve information and gradients. After combining, the result is normalized to ensure the values remain consistent and within a manageable range. This normalization prevents issues like exploding or vanishing gradients, thereby enhancing the learning efficiency and stability of the neural network. Moreover, the LSTM decoder is excellent at handling sequential data and capturing temporal dependencies, but sometimes the direct influence of certain variables is more beneficial if they are not processed sequentially. By bypassing the LSTM decoder, the model can preserve the integrity of these crucial features and ensure that they have a direct impact on the final prediction. This improves the model's ability to make accurate forecasts by combining the strength of both sequential processing through the LSTM and direct influence through bypassing variables. This process is repeated for each subsequent time. So x t plus 1, t plus 2, t plus 3, etc. So t plus tau. The variable selection, LSTM decoder, add, and norm gate work together to ensure that the model continuously adapts and makes accurate predictions by leveraging both path and known future inputs. Moreover, please note that we are still talking about future known inputs, which is inputs that we know will repeat over time, again, day of the week, holidays, etc. Now, we have been talking about the future, but we also need to understand the past, and this is where the LSTM encoder comes into play. The LSTM encoder processes past inputs to capture and encode temporal dependencies into a fixed length context vector. And this context vector summarizes the information from the entire sequence, which can then be used for various downstream tasks. While the LSTM decoder focuses on generating future predictions, the LSTM encoder is responsible for creating an informative and compact representation of past sequences. And this way, the model can effectively use both past and future information to make accurate forecasts. So, in other words, the LSTM encoder captured past data, the variable selection identifies key features, and the LSTM decoder predicts future values with an add and norm gate ensuring stability and efficiency. Together, they form a powerful architecture for time series forecasting. At the same time, we need to have in mind that we don't just have one past input, but several. Furthermore, if you recall the LSTM section, it is not so different. So this is where we now move into the next stage. So up until now, not very different from LSTM, but now it will be. So let's get started. The next component in our TFT model architecture is the GRN, or Gated Residual Network. The GRN, or GRN, I don't know which way is bad. I think GRN is fantastic, but GRN should be a bit better, I guess. So the GRN is designed to enhance the network's learning capability by managing the flow of information through gating mechanisms. Now, here is how it works. Gating mechanisms controls the flow of information, allowing only important signals to pass through while filtering out irrelevant data. As well, residual connections. These connections add the input of a layer to its output, helping to preserve important information and gradients. This is very similar to the concept used in the add and norm gate. And finally, normalization. This ensures that the outputs remain consistent and within a manageable range, stabilizing the training process. So by integrating the GRN into the TFT model, we can ensure that the network efficiently manages the flow of information, focusing on the most important features and maintaining stability throughout the learning process. Now, let's talk about the masked interpretable multi-head attention part of the TFT model. This component is absolutely key for understanding how the model captures complex dependencies and interprets them for better predictions. The masked interpretable multi-head attention, this is a mouthful, this is an advanced mechanism that helps the model focus on different parts of the input data simultaneously. It uses multiple heads to look at different parts of the data, allowing it to capture various patterns and relationships within the data. So this multi-head is then flagged with the multi-arrows here. And therefore, why does it have 3 arrows? And this is because the arrows indicate the multiple heads used in the attention mechanism. So each arrow represents a different head focusing on a different part of the input data. So this multi-head approach ensures that the model can capture a wide range of dependencies and relationships. And this makes the predictions more robust and more accurate. But how does it work really, right? So the attention mechanism assigns different weights to different parts of the input data and highlighting the most relevant information while downplaying the less important parts. And it's this selective focus that helps the model make better predictions by concentrating on the most critical pieces of information. To sum it up, the masked interpretable multi-head attention mechanism, so it enhances the model's ability to capture complex patterns and dependencies within the data, improving the overall accuracy and interpretability of the predictions. This is a crucial part of the TFT model that allows it to effectively process and analyze large sets of time series data. Now, after this selective attention, the processed information flows to the next add a norm gate. This gate combines the attention-enhanced data with residual connections from previous layers, ensuring that crucial information is preserved. The combined data is then normalized, maintaining consistent and manageable values, which stabilizes the training process and enhances learning efficiency. However, the output of the gated residual network, GRN or GRN, might bypass the MIMA, so the masked interpretable multi-head attention, and go directly to the next add a norm gate for several reasons. Why? Firstly, the GRN already defines and refines and as well filters the most important information, making additional processing by the MIMA unnecessary for these critical signals. Secondly, skipping the MIMA reduces computational complexity and speeds up the processing, which is beneficial for time-sensitive predictions. Lastly, bypassing the MIMA can prevent overfitting by avoiding excessive attention-based adjustments, thereby preserving the integrity of crucial features and ensuring they directly impact the final prediction. Next up, the GRN processes the outputs, further refining the information. The GRN ensures that only the most relevant information is passed forward by filtering out the noise and preserving the essential data through its gating mechanism. And by doing this, the GRN maintains the quality and relevance of the data, enhancing the model's ability to make accurate predictions. And this refined output then moves on to the subsequent add a norm gate, continuing the cycle of processing and refinement throughout the model. Now, let's talk about the final stage of the TFT model architecture, the dense layer and quantile forecasts. After passing through the multiple layers of the model, the processed data reaches the dense layer. The dense layer applies a final transformation of the data, think like an activation function, and integrating all the learned patterns and dependencies. And this layer is crucial for generating the final predictions. The quantile forecasts represent the model's predictions for different quantiles, providing a range of possible future values. This is especially useful for understanding the uncertainty and variability in the predictions. By generating forecasts for multiple quantiles, the TFT model can offer a more comprehensive view of future outcomes, helping to make more informed decisions based on our predicted range of values. Now, we need to talk about static covariate encoders, which also play a crucial role in the model by encoding static features that do not change over time, such as location, type of product. These static features provide important context for the model, helping it understand the broader characteristics of the data. The static covariate encoders are connected to multiple layers of the TFT model because they provide consistent, unchanging information that needs to be accessible at various stages of processing. By enriching the model within this static context, the TFT can make more informed and accurate predictions, leveraging both dynamic inputs and stable long-term features. In the chart, the Temporal Fusion Decoder is responsible for synthesizing information from past inputs, known future inputs, and static covariates to produce the predictions. It does this by using advanced components like the attention mechanisms that we talked about to ensure that the most relevant information is emphasized and the model learns the best way possible. The decoder combines these inputs to generate the final predictions while considering the dependencies and patterns in the data. The position-wise feed-forward layer in the chart applies a series of linear transformations and activation functions to each position in the input sequence independently. This layer processes the data after it has been refined by attention mechanisms, ensuring that non-linear relationships and complex patterns are captured. By applying these transformations, the model can better understand the interactions between different time steps without altering their temporal order. The temporal self-attention mechanism, shown here in the chart, allows the model to focus on different parts of the input sequence simultaneously. This mechanism assigns varying weights to different time steps, helping the model identify and emphasize the most relevant information. Again, emphasizing the multiple arrows indicate the use of multiple attention heads, each focusing on different parts of the sequence, which enhances the model's ability to capture the long-range dependencies, which will hopefully then improve our accuracy. Then we have the static enrichment. If you didn't see it, it's over here. It's the last part of the Temporal Fusion decoder. And this involves incorporating the static covariates into the model. So these covariates, the ones that are constant over time. And the static covariate encoders process these features and integrate them with the dynamic temporal units. And this enriches the model understanding and allowing it to make the decisions. And this step ensures that both stable and variable aspects of the data are considered. The chart shows that the output from the first add-a-norm gate can also bypass the Temporal Fusion decoder and go directly to the add-a-norm gate. So all of this here in the end may be bypassed. It's a possibility. This bypass occurs because the initial processing may have been already good enough, so refined enough, and all the critical information has been processed. So skipping these additional layers can reduce the computational complexity, speed up processing, and avoid overfitting by not doing unnecessary adjustments. In Darts, the bypassing of the Temporal Fusion decoder by the output from the first add-a-norm is handled automatically, right? So this is not something that we need to care about. It's a possibility, and the Darts does take care of it. Now, let's sum it up. We are almost at the end. The TFT architecture synthesizes information from past inputs, known future inputs, and static covariates to produce accurate predictions using advanced components like attention mechanisms and gated residual networks. The process begins with a variable selection, followed by the LSTM encoder to capture past data, LSTM decoder generating future predictions. The add-a-norm gate ensures stability and efficiently by combining outputs and normalizing them. The gated residual network enhances the learning capability by managing the information flow. While the MIMA, so the masked interpretable multi-head attention, focuses on different parts of the input data simultaneously to capture the patterns and dependencies. The dense layer applies a final transformation to generate predictions, and the quantile forecast provide a range of possible future values, enhancing our predictions. Static covariate encoders provide context and integrate consistent information throughout multiple model layers. Finally, the TFT model allows output from the first add and ARM gate to bypass the Temporal Fusion decoder and move directly to the last add and ARM gate. This bypass occurs when the initial processing has sufficiently refined the critical information, reducing computational complexity, speeding up the process, and preventing overfitting. DARTS handles this, bypassing automatically within the model architecture. And now, I know it was long, but I really hope that this big deep dive would be the way to go there to fully explain this TFT architecture. Thanks, and I'll see you in the next video.